This webcast discusses problems that involve circular orbits and the energy of satellites in circular orbits. Okay, so in the first problem here, we're talking about the moon, which has a roughly circular orbit with regard to the around the Earth, and it's giving us the radius of that orbit. Now notice they've already calculated the radius for us. I do not have to add an altitude here to the radius of the Earth. That is this distance, 3.84 times 10 to the 8th meters. That's the distance from the center of the moon to the center of the Earth. And then they're giving me the mass of the moon and the mass of the Earth. And they want us to find the orbital speed of the moon. Well, the equation that applies here is the speed of a satellite, which is the square root of universal gravitational constant multiplied by the big mass, that's the mass of the object at the center of the orbit, divided by the orbital radius. This equation came from this slide here, right, where we were talking about the orbital velocity for things that are in a circular orbit. Okay. So I take the universal gravitational constant, which I know is 6.67 times 10 to the negative 11th. I multiply it by the big mass. That's the mass of the central body. Both of these masses are very big, right? But the Earth is in the center of the moon's orbit, and its mass is a little bigger, right? It's times 10 to the 24th instead of times 10 to the 22nd. And then I'm going to divide by the orbital radius. And I'll put all of that in under my square root. Okay, so let's see what this is. I'm taking the square root of 6.67 e to the negative 11th times 5.97 e to the 24th, and then dividing by 3.84 e to the 8th. And so I get 1018.320 meters per second. That is the tangential velocity of the moon as it goes around the Earth. Okay, then we have one regarding the International Space Station. They're giving it the mass of the space station, and they're saying that it orbits the Earth at an average altitude of 362 kilometers. We're going to assume that the orbit is circular, and we want to calculate the orbital speed. Okay, so again, the relevant formula is the speed of a satellite in circular orbit. Okay, but I have a couple of things here. I need to find the orbital radius because they did not give me that. They gave me the altitude of the space station. And so I need to take the radius of the Earth and add the altitude to find that orbital radius. So let's see, the radius of the Earth is 6.38 times 10 to the 6th meters. And look here, they gave me the altitude in kilometers. That's very common. I need to convert that to meters, right? So there are 1,000 kilometers in a meter, and so 1,000 meters in a kilometer, and so I'm going to add 362,000. So the total orbital radius here is 6.38 e to the 6th plus 362,000. And that's 6,742,000 meters. Okay, now I'm ready, I think, to plug into this formula, because I know that the universal gravitational constant is 6.67 e to the negative 11th. Okay, I have to decide which mass to use. They gave me the mass of the space station and the mass of the Earth. Well, this is an uppercase M. I know that for this equation I need to plug in the bigger mass. It's the mass that's in the center of the orbit. And so here that would be the mass of the Earth. And then I'm going to divide by that orbital radius. Okay. And so I get 7,685.209 meters per second. It's interesting to look at these two problems together because both the Moon and the International Space Station are satellites around the Earth. The Earth is at the center of their orbits. Notice how much faster the space station is going than the Moon. That's because the space station is at a lower altitude. It's closer to the Earth. So to stay in its orbit, it has to move faster. Okay, let's see here. Now we've got a satellite that's in circular orbit around Io. That's one of the moons of Jupiter. And they're saying that the satellite is at an altitude of 320 kilometers above the surface of Io. They're giving us Io's mass and Io's radius. So it says, what's the velocity of that satellite? Well, they gave me a kilometer, an altitude in kilometers. And so I know that to find the orbital radius, I need to add the radius of the central planet, that would be the radius of Io, plus the altitude. And let's see, so the radius of Io is 1821 kilometers. All of these things have to be put into meters. So that would be 1821,300 meters plus 320,000 meters. And so the orbital radius is 2,141,300 meters. Okay, then I can use the formula for the orbital velocity of a satellite. So the universal gravitational constant is 6.67 e to the negative 11th. Okay, which mass do I use? They've given me the mass of the satellite, 430 kilograms. They also gave me the mass of Io. And this is the big mass. It's the mass of the body at the center of the orbit. So that would be Io, which is 8.932 e to the 22. And let's see, and then the orbital radius that we just found, and so I get 1,668.009 meters per second. Okay, and then it says how many hours will it take the satellite to make one full revolution around Io? We're talking about the period, right? The time to make one full revolution. And I know that the period is the circumference divided by the tangential velocity. Okay, so here the radius of the orbit is the orbital radius that we calculated up above. That's so 2 pi times that orbital radius is the total distance that the satellite has to go, and it's moving at the velocity that we just found. So here I'm going to have meters, and here I'm going to have meters per second. And so what's going to happen is that the meters will cancel, and this will give me my period in seconds. So let's get that. It's 2 times pi times the orbital radius, and then I'm dividing by that orbital velocity, and I get that the period is 8,066.012 seconds, but it's asking me how many hours would it take, and so I need to convert here. So I've got 8,066.012 seconds, and I know that there are 3,600 seconds in 1 hour. And so it would take that satellite 2.241 hours to make one full revolution around Io. Okay, and let's do the last problem here. Here we've got a satellite, and they're giving me its mass. It's in orbit around a planet, and they're giving me the mass of the planet. They're saying that the satellite has an altitude of 140 kilometers above the surface of the planet, and then they're giving me the radius of the planet. So first they're saying, what's the magnitude of the gravitational force that the planet exerts on the satellite? Gravitational force, that's G times the product of the masses divided by the distance between them squared. I better find the orbital radius. They didn't give that to me, and I'm probably going to need it here. So that's going to be the radius of the planet plus the altitude. So the radius of the planet in meters is 6,400,000. The altitude was 140 kilometers, which is 140,000 meters. And when I add those together, I get an orbital radius of 6,540,000 meters. Okay, so I can start doing this. The mass of the planet is 5.7, 10 to the 18th. The mass of the satellite, the little mass, is 3.2 e to the 4th. The orbital radius is 6,540,000. And remember that that needs to be squared. So let's see what we get. And so I get 0.284 newtons. It's very little. Okay, so then it says, what is the gravitational potential energy of the system comprising the planet and the satellite? So I remember that the gravitational potential energy of a satellite, it's always negative, right? And it equals, and we'll go remind ourselves of that equation. It's negative G times the product of the masses divided by R. Okay, so the same masses that we had before, but now I'm dividing by R, but I'm not squaring it. And so I get negative 1860256 and this would be joules because it is energy. That's the gravitational potential energy of the satellite. Then it's saying, what's the orbital speed at that altitude, right? This is the same altitude that they told me above. Well, that formula is the square root of g times the big mass divided by the radius. So let's see here. The big mass is the mass of the planet. The r is the same orbital radius that we calculated. And remember to take the square root. So I get 7.625 meters per second. Okay. So it says when it's at that altitude, how many minutes does it take for the satellite to make one full revolution? So I'm finding the period, which is the circumference, divided by the orbital speed. So the circumference is 2 pi times that orbital radius that we found. See how we keep using that same orbital radius? And I'm dividing by the velocity we just found. This is going to give me seconds, right? The 2 meters will cancel. So I will have to convert. So I've got 2 times pi times the orbital radius, and then divided by the velocity that we found. So I get a lot of seconds. 5, 3, 8, 9, 4, 7, 1. And then I need to convert. There are 3,600 seconds in 1 hour. Oh, we want to make it minutes. Sorry. I was thinking hours. Let's do minutes. So there's 60 seconds in 1 minute. And so it's 89,824.518 minutes. Okay, then they want to know what's the kinetic energy of the satellite. Well, the kinetic energy of the satellite is positive, and it's g times the product of the masses divided by 2r, or I could say it's 1/2 of the absolute value of the gravitational potential energy. Since I've already calculated the gravitational potential energy, that's what I'm going to do. So I'm going to have half of, but it has to be positive. And so I get 930,128.441 joules. So that's the kinetic energy of this satellite. What's the total energy? Well, the total energy is negative g times the product of the masses divided by 2r, or I could say it's negative the kinetic energy. So it's going to be negative that amount that I just found. Okay. And then the last one here is how much energy would be required to boost the satellite to a higher orbit. So we started at an orbit of 140 kilometers, and now we want to move it to an altitude of 1,000 kilometers from the surface of the planet. Okay, so what I want to find is the change in the total energy of the satellite. And that's going to be the total energy at 1,000 kilometer altitude minus the total energy at the 140 kilometer altitude. Okay, so I need to find the orbital radius at the higher altitude. And so that would be the radius of the planet plus 1,000 kilometers. So let's see, the radius of the planet was 6,400,000. And now I'm adding 1,000 kilometers, which is 1,000,000 meters. And so now the orbital radius will be 7,400,000 meters. Okay, I already know the total energy at 140 kilometers. And so I don't need to recalculate that, but I do need to find the total energy at 1,000 kilometers. And that would be negative g times the product of the masses divided by 2r. And let's see, the mass of the planet was 5.7 e to the 18th. The mass of the satellite was 3.2 e to the 4th. And now I'm at this higher orbital radius, which is 7,400,000. And so I get negative 822,032 joules. So finally I find that change in the total energy. It's going to be negative 822,032 minus the negative 930,128. So notice I'm subtracting a bigger negative number, and so I am actually going to get a positive amount of energy here. And I get that it would take 108,096 joules of energy to move the satellite to that higher orbit.